I also looked the replay marks, the function marks, and everything, but I have had no time to write them here. They are in my file, so perhaps later, after I explain the new material, after that I might, I don't know what, write down the marks in the paper, or you can just come and ask me quietly. Ooh. End of term is always crazy time for all teachers. I don't know how we can say. Okay. Does anyone need the paper from yesterday? Anyone who wasn't here yesterday? Is there anyone who didn't get the paper yesterday? Who wasn't here yesterday? What? Anybody else? Okay, so here we have the old papers if anyone needs those. Okay. What now? As I told you yesterday, yes, I had them. I have them not on that paper. I have them in my file. So after I explain the new material, I don't remember what about you. You passed probably.
No, that's it.
Okay. Second derivative. So the derivative of the derivative. What does that part tell us? So if I have the function y equals f of x, I can derive it. I can find the derivative of any function, and this derivative will tell me quite a lot of things, as we saw yesterday and last week. It will tell me about the behavior of the function. It will tell me where the function is increasing, where it's decreasing. It will tell me where, or if any, the maximum points or minimum points are. Some inflection points, for example, horizontal inflection points or vertical inflection points. But I mentioned already yesterday that we might have some other inflections just as well. And we might need some means to decide where those other inflection points are. So if we can compare the derivative to velocity in motion, velocity or speed, then the second derivative is obviously, yes, it's the acceleration. It's the velocity of the velocity, the change, the rate of change of velocity, in other words. So I can find the second derivative by taking the first derivative and deriving it again. So I generally write it like this, or I can write it as like second derivative by dx squared, denoted this way. And of course I can, oh yes, two dots. Yes, two dots. You can also do two dots. Yes. No. You can write them. I'm not a physicist.
Yeah.
Okay. Happy now? Alright. So actually you can find as many derivatives as you like. No, that's not true. As many derivatives as the function will allow you. Because sometimes you might just have to stop deriving because you get zeros. So starting with some moment, starting with some derivative, all the next derivatives would be zeros. Or it depends on the behavior of the function from point to point. Anyway, we are concerned with the second derivative, which is in motion. It corresponds to acceleration, or the rate of change of velocity. if velocity corresponds to the derivative. But for the shape of the graph, actually, we can use the second derivative in exactly the same manner as we use the first derivative for increase, decrease, and maximum, minimum points. In other words, we have a rule. If the second derivative of the function is, let's say, positive in some neighborhood around the point x0. Obviously, a single point alone doesn't really matter. What matters is the behavior of the function close to that point, because we can never just pluck out one single point, take it out of the graph and say, see, the function behaves like this. A function never behaves at a single point. It's always, even when we say the function is increasing at this point, or the function is doing this at that point, we always think in comparison to some other points in the closest neighborhood of this point. So when I write this, I actually mean that there is some neighborhood close to this point x0. So around this point x0, there is some neighborhood in which the function behaves in this manner. It might be a very small one, but still, I can never consider a single point alone. I can never take it out of the context. And the context in this case would be all the other points and all the other points on the graph. So, if the second derivative is positive, then we say that the function is concave down. That would be the calculus description of concavity. Concave up, sorry. Concave up. The cavity is pointing upwards. Concave up. This is called concave up. If the second derivative is negative at some point, or actually more likely in some neighborhood or in some segment, then we say the function is concave down. The shape of the graph is like this. The cavity is pointing down, so we say concave down. Geometrically, what does concavity up and concavity down mean geometrically? It means if a function is concave up, it means that all the tangents we can draw, if all the tangents we can draw in this segment are below the graph. See, if the function is increasing, then this type of graph, the function is increasing and concave up. And we see that at every point where we can draw a tangent line, the tangent line is below the graph. And if the function is decreasing and concave up, again the same thing. I can choose any point on this graph and draw the tangent line. And the tangent line is below the graph. So that would be the geometrical description of concavity. Analytically or calculus-wise, we consider the second derivative, and then we start thinking, what does it really mean? So we need to understand geometrically how to describe concave up, concave down. So concave up means that all the tangents are down there, below the graph. Concave down, all the graphs, all the tangent lines are, wherever we draw the tangent line is above the graph. So concave down means that all the tangents are above the graph in that particular segment, obviously. So how can we explain that? If the second derivative is positive, why would we say the function, the graph is concave up? Why? If we compare the situation to the geometrical view, so we can see that as we go on, the slope is increasing. You can see the slope is increasing, which means the rate of change of the derivative is increasing. The derivative is increasing, which means the derivative of the derivative is positive. Now, it can get confusing if you are not careful with your thoughts. The same actually here, even though the lines become more and more horizontal, the gradient is actually increasing from -3 to -2 to -1 to 0. So again, it's increasing. The second derivative, the value of the derivative is increasing, which means its derivative is positive. And the same or a similar thing for concave down. If the second derivative is negative, then the first derivative is decreasing according to what we had yesterday. And we can see, yes, for example, from 0 to something negative, more negative. So yes, the second derivative, in this case, the first derivative is decreasing, and the second derivative, therefore, the second derivative must be negative. And of course, the points between the parts of the graph that are concave up and concave down are called inflection points. Inflection points. Sometimes they spell it with an X.
Ah, yeah.
Sometimes they spell it with an X. Different countries, different textbooks, different authors.
Yes.
You can choose whichever you prefer. I can never choose, so I sometimes write one way, one day, and the next day I might write the other way. All right. We can explore the second derivative in a manner similar to the first derivative to decide about the shape of the graph concavity-wise, curvature-wise. So if the first derivative tells us whether the function is increasing or decreasing, or perhaps it has a maximum minimum points, then the second derivative actually tells us that the function might be curved upwards or downwards, concave down, concave up. And so we actually need both the derivatives to deduce the actual perfect shape of the graph. And of course, there's always the possibility that the second derivative cannot help us in some situations. We'll see those soon, in a short while. So let's have an example to see how we can use the second derivative. How we can use the second derivative to investigate the shape of some functions. The first example, f of x is x cubed minus 2x squared minus 4x plus 8. So to find the second derivative, of course, obviously, we have to find the first derivative. So the first derivative is 3x squared minus 4x minus 4. To investigate the shape of this, we would obviously need to find the potential minimum maximum points. That's one thing that we should discover. So if we ask that this derivative equals 0, it happens for, what are those? Minus 12, 6, minus 2, 2, and minus 2/3. Okay, so we can solve this equation and see that 2 and minus 2/3 are potential extreme points. They are stationary points. We don't really know whether they are minimum points, maximum points, horizontal inflection points. But we'll see a little bit later. So the second derivative is, we take the first derivative, derive again, 6x minus 4. So we see that the second derivative is 0 if we have x, let's say a third, interesting x value, simply 2/3. And now we can try and see how this information, how these two derivatives and the critical points can help us to explore the shape of the graph, and actually to how can these two enable us to sketch a graph quite accurately. So you don't have to sketch graphs point by point always, but if you explore the two derivatives, and if you make the correct conclusions, you can sketch a graph of a function quite accurately without actually plotting every point. Alright, the first derivative. So the two critical points, minus 2/3 and 2. So the first derivative. What about signs? What about signs? Do you know the signs all at once, or do we need to guess or do something? Plus, minus, plus.
Yeah.
You have to remember that this is a quadratic function. So we can imagine that the parabola, you see, ends would be pointing up. If I sketch the graph of the derivative, it would be a parabola. The ends of the parabola would be pointing upwards, and these are the zeros of that function, the intersections. So it would be positive here, below the x-axis here, and above the x-axis there. So this tells me that the function itself is increasing, decreasing, increasing. So this will be the minimum point 2 and something, and this will be the maximum point minus 2/3 and something. And yes, I'm going to cheat and look at my paper. Where do we have it? Maximum point minus 2/3. All right, 9 and 13 over 27. Horrible number. And if x is 2, then we have 8 minus 8 plus 8, 0. Okay, so this was the first derivative. Now let's apply the second derivative. So what we discovered from the second derivative, the point 2/3, and I'm just putting it so that it is located correctly between minus 2/3 and 2. I make sure that these two diagrams are coordinated, that they work together. The second derivative would be, of course, if x has a large value, then the second derivative will be positive, and if x is very small or negative, then the second derivative is negative, which means the graph of the function is concave down, concave up. How can we remember which way the concavity points? Okay, if the second derivative is positive, we are happy. And so we know that the concavity is up. If the second derivative is negative, we are unhappy, we have a sad face, and so the concavity is pointing down. What's funny?
You have it in the paper. Happy face and sad face.
Yes. So why not? It's a very good way to remember. It's a very good way to memorize this. Second derivative, positive, happy, concave up. Negative, unhappy, sad, concave down. So think about a smiley face and you have your answer. So for this, I can say that, first of all, the function is concave down, increasing, it reaches its maximum, it's still concave down, then it starts decreasing, then it reaches the inflection point, which is not a stationary point because we see the function is still decreasing, and then we have an inflection point that becomes concave up, and still goes on decreasing until it reaches the minimum and goes up again, increasing, but still being concave up. So you have, I think you have the graph. Yes, I have given you the graph there. And I have given you the graph there on the second page. The other side. You see, the point A corresponds to the maximum point, minus 2/3, 9, and 13 over 27. And 2, 0, the point B corresponds to the minimum point. And finally, point C is actually shown where the inflection point is. You can see that the graph is concave down, and somewhere there, it's pretty stretched vertically, so it's not easy to see that that point is indeed exactly the inflection point. So I should probably have flattened this graph some more. I already did it. All right. So this is how we can analyze the shape of a function. Another problem with which can be solved sometimes using the second derivative. We can see if a point is stationary and the function is concave down, then obviously it must be a maximum point. So we have actually a very nice rule. We can deduce a very nice rule. If the function at some point, the derivative is 0, so the tangent is horizontal, and at the same point, the second derivative is negative, then we can say that this must be a maximum point. Horizontal, tangent, and concave down. Then obviously it's a maximum point. And in a similar way, if we have another the stationary point where the second derivative at this point is positive, then obviously we have this situation. It must be the minimum point at that point. We have problems if the second derivative does not exist at that point. Well, it should. Or if we see that the second derivative is also equal to 0, it happens to functions that are very flat at minimum or maximum points sometimes. For example, if I take the function y equals x to the fourth, I could say, all right, the first derivative is 4x cubed, so it's horizontal, the tangent is horizontal at the point x is 0, but at the point x is 0, if x is 0, we see the second derivative is also 0, so it tells us nothing. It doesn't tell us whether there is a maximum or minimum point. We can't really see. In this case, the second derivative equal to 0 means that at that point the graph is simply flat enough for something, for what? So that the second derivative is equal to 0. In this case, we should probably determine the minimum-maximum situation using the old method. So if x is 0, then I can see that for positive x values the derivative is positive, for negative x values it's negative, so I can see it's a minimum point. Because this does not give us any information about minimum-maximum in this situation. So sometimes, if you don't need to investigate in which intervals the function is increasing or decreasing, if you are only interested in minimum maximum points, or if perhaps the signs of the derivative are difficult to analyze, if it's an unpleasant expression where you can't tell the signs easily, then you might just find the second derivative and put in the x0 value. You found x0 from this, put it in there, and simply you don't even have to evaluate it precisely. All you have to see is whether this second derivative would be positive or negative. So from this we find x0, then we put it in the second derivative and check the sign. And the sign will tell us whether this point is maximum or minimum. But it doesn't always give us an answer. So this method, unfortunately, does not always work. Only sometimes. Okay, so we should probably have a look at some exercises and then at least one application of derivatives. Problems of optimization. So we combine the information from the two derivatives to investigate the shape of the function. All right, let's have a look. Find the first 4 derivatives in exercise 1. Okay, for which function would you like to find the first 4 derivatives? I think A would be boring. The derivative of sine is cosine, the derivative of cosine is minus sine, then the derivative of minus sine, and so on. So perhaps A could be left for homework. Perhaps we could do B or C or D, whichever. See? Okay, remember that when you derive b, you get to multiply by 2 every time, because it's a composite function.
So we
C. Alright, C. 4 derivatives of 2x plus 3. First derivative, a composite function. So the outer function is ln. The derivative of logarithmic function is 1 divided by 2x plus 3, and then the derivative of the inner function is just 2, and we have to multiply by it. Like this. Chain rule. Alright, now the second derivative. Yes. So should we can apply chain rule again, or we can apply the quotient rule.
It's 4 over this thing square.
No, it's actually minus 4
Minus
over.
4 over.
Minus 4 over. Alright, so we can think of this in terms of chain rule, because this function is actually this to be derived. So 2 is the constant factor in front. It doesn't change anything. Times minus 1 times 2x plus 3 to the power of minus 1 times, yes, chain rule, the derivative of 2x plus 3 again, 2. So now we have minus 4 times 2x plus 3 to the power of minus 2, or minus 4 over 2x plus 3 squared. Remember the meaning of the negative exponent. For example, like this. Or in some other way, if you remember, I did give you a special case for the quotient rule. If I have a function 1 over b derived, I think, show you this. I did show you this, I think. Perhaps not, no?
We just use v
All right.
power minus 1.
Well, we can use this. No problem. So the third derivative, let's use this to find the third derivative, this one. So it would be minus 4 times minus 2 times 2x plus 3 to the power minus 2 minus 1 times, again, the derivative of the inner function, which is 2. Now we have minus times minus, now it's positive, 8 over 2x plus 3 cubed. And it's only the third derivative? Okay, we need one more. So we can write them in the Roman 4 shape, or we can, the higher derivatives can be indicated by, let's say, 4 in brackets. 4 in brackets. Instead of writing 3 primes, we can write 4 in brackets, the fourth derivative. So 8 remains as it is. Now we multiply by minus 3. It will be 16. No, 8. Sorry, yes, 16. Because we had, yes, 16. Right. 16, so I have to write 16 here. Times minus 3, 2x plus 3 to the power minus 4 times 2 again. So now we have minus 48 times 2, 96 over 2x plus 3 to the 4th. And so on and so on. Wouldn't be so easy, wouldn't be so difficult to go on and on and on. The only problem is that these numbers would become greater and greater. So it wouldn't be very convenient to write and to calculate. Because we can see that these factors would increase, minus 1, minus 2, minus 3, we have minus 4, minus 5, minus 6, and times 2, times 2, times 2, times 2. So it would increase quite quickly. Actually, we see that there's the factorial involved. You know what a factorial is?
Yeah.
Okay. Okay, I can go on. Alright, so mostly it's chain rule, but sometimes you get to repeat the product rule, sometimes you might get to repeat the quotient rule again and again and again.
Let's do the third exercise.
The third exercise, yes, I meant to do this. So an example of graph means it doesn't have any specific graph, simply showing clearly whether the function increases or decreases, whether it's positive or negative, and concave up or down. So in A, I will try to do them all in one graph. So X, Y. And so AB, for example, here, AB, the segment AB, and let's see. Y is positive means the function is above the x-axis. Y, the function is positive means it's above the x-axis. The derivative is positive means the function is increasing. So I can say perhaps the value at A is this and the value at B is this. And the second derivative is negative. The graph is concave down. So the example would be this. That's all.
What's that?
3a.
No, the right side.
This?
Nothing.
Second derivative, sad. The very sad second derivative. Okay, this is the situation A. Now let's have a look. I do have 4 colors. B, y is still positive, so the function value is positive. The second derivative is negative, which means the function is decreasing. So I might do something like this and this. For B, the function is decreasing. And the second derivative tells us, oh, the second derivative is positive. Don't look. So this is B. The function is positive, it's decreasing, and the graph is concave up because the second derivative is positive. And if you like, you can sketch each of these separately or all in one picture, doesn't matter really. C, the function is negative, so it will be below the x-axis. The first derivative is positive, so it will be increasing here to there, the function, for example. And the second derivative is positive, same situation, so it will be like this. For example.
You're taking the points
I'm taking the points because you see the task states in a segment from A to B. I'm not interested in what happens outside the segment because the function must be increasing in the whole segment. So I put the function value at point A lower than the function value at point B to show that it will be increasing. And now all I have to do is sketch the example of a graph. It's not an accurate graph. As I said, these are simply examples that should tell you the behavior of the function. Of course, it could be much steeper, but we only need some examples so that you see how both derivatives affect the shape. What do the derivatives do to the shape of the function? Or rather, the function is what it is. The two derivatives show us the shape of the function. The two derivatives by themselves, they do nothing. They simply are facts that describe the situation. This is C. Yes, oh, I didn't write. Yes, this is C. And finally D. The function is positive again. The first derivative is negative, which means the function is decreasing. So it goes down, from A to B it goes down, decreasing. And the second derivative is negative. Start again. Like this, for example. So this is D. So simply combining the information we got for each from each derivative, in each segment we actually can sketch the graph of the function, or at least sketch symbolically, just sketch an example. It doesn't have to be an accurate drawing, an accurate graph, but we can at least understand the behavior of the graph, the behavior of the function, if we consider these. Okay, second derivative to determine the extremum in 4, we should look at an example.
And you are using only first and fourth quarter. What about the others?
It doesn't matter because AB, the task didn't tell us where this segment from A to B is. So I chose to put it on positive x-axis. I could have put it here, I could have put it part there, A negative, B positive. It doesn't really matter. Because in this case, what matters is the shape. What matters is the shape and our understanding whether the graph is above the x-axis or below the x-axis. So how the signs, the three signs of three functions, the function itself, its derivative, and the second derivative, how those signs describe the function. Of course, to know more accurately, to know the function more accurately, we need to know the values of A and B, the formula of the function, the equation, and then we could calculate this value, and perhaps one or two intermediate values to sketch the graph more accurately, which is what we will do next week. Now let me think, it's
Next
Tuesday, today it's Tuesday, we have this. So on Thursday we'll talk about asymptotes, on Monday we'll investigate graphs, complete investigation of functions. On Tuesday we will just do exercises and consultation if necessary, and on Thursday, on the last day, then we can write the test. Or if you want, we can try writing on Tuesday, and then that leaves Thursday for what? Retakes? Retaking? Oh my. Oh my. Do you know which date the exam is? I don't.
Yeah.
What?
The examination date? I don't know. I have no idea.
Shame on you.
No, they haven't told me.
Ninth.
But they have,
They
you're not using this.
didn't tell me. They asked me which days I would prefer. I told them, but I never got any feedback. So,
Okay, give me a second.
and I always forget to email and ask.
I was checking them, but I forgot now. But you.
Is it the 9th?
Yeah,
I think so.
8th.
8th.
There are 2 days.
8th of
One for consultation.
One for
and then
consultation and one for.
Yes, so 8th and 9th?
8th.
So eight
Let's see, the 5th is Monday, I think. Is it? The 5th of January should be Monday, I think, because it's
it's Monday.
back to school.
It's Monday.
The Monday. The 5th is on Monday, so the 9th is Friday, and the 8th, the consultation is Thursday. All right.
No,
What
it's-
time?
Oh
have
no,
they
it's
put-
the exam.
It's a written exam on 8th,
Yes.
but there is no consultation. Time.
There's no consultation.
Should be.
No.
There should be consultation time the day before the exam.
No, we don't have. We have on the 8th consultation for economics, then exam of mathematics.
On the 8th.
8th. On the 9th we have economics.
8th is Thursday.
There is no consultation.
No
No
consultation.
consultation. We have only an additional exam at the
There
13th,
should be. That's the retake. 13 what?
Additional.
13th
The
January.
13th. The 13th is Tuesday. Okay. So, well, it's not good because you should have a chance for a consultation before the exam. Monday the 6th.
And there's not much.
Tuesday the 6th. Perhaps. No, I'm just. Or
This is
some
indication.
normal lecture time. We could do it Tuesday the normal lecture time this time or before the exam or Wednesday before the exam, if the exam is on Thursday.
Maybe on 5th.
Fifth?
Maybe.
Okay, I have to think. Fortunately, we have some days to decide this because I don't like the idea that you don't have a consultation time because some people might want to grab a chance if they miss only, we have only one task, one test missing, perhaps they want to try to, although the last day, oh, it's not the last day before the exam then, if we don't do it the day before.
We have additional exam on 19th.
So are you counting on failing the first? Are you counting on failing on the 8th? So I plan to fail on the 8th so that I can come on the 19th. That's again silly. Okay. Now, second derivative. So this is we have to consider. We have absolutely there's enough time to cover all the material necessary, and we might of course write the test on Tuesday. Because we need 2 more lectures to look at asymptotes and investigating functions using the graphs, and then we have 1 day, let's say Tuesday, for practicing, for exercises, for consultation, and everything before the test. Or do you want to take a chance on Tuesday and then see, perhaps on Thursday you can use that for retakes and I don't know.
Yeah, it's better.
So you mean the test for this section?
Yes, for this section.
Oh, well, I thought it was the final.
So we can do the test on this section, which will also include a full investigation of one function, including asymptotes, minimum, maximum. This.
And what will it be?
What about
Well, I'm just trying to decide. I'm asking you. I had planned to do it on Thursday and to keep Tuesday before Thursday for practice exercises because I have a suspicion that some people would like to practice some more. On the other hand, I know how anxious you are to get your good grades and retake if possible and all that.
It depends, like, how long we will get the result.
If we write on Thursday, when will be corrected?
If you write on Thursday, it will be corrected. Well, I will do it on Friday, obviously, because on Friday I don't have lessons at school, I don't have lectures at the university.
But we will not be able to.
Yes, last day 19th.
I will have to, in that case, after that. So once a semester, I do make an exception, and I email everybody their marks, the full line of 1, 2, 3, 4, 6 marks, and if I offer, then the mark I offer automatically. So that would be, if I have to do that, then probably it would take a couple of days to get all my papers in order. But, okay, think about this, and we'll talk about this more on Thursday and decide for sure.
And
Yes,
in the beginning of this semester, you said like we have
yes. 2 homeworks, 4 tests.
you have there's a little marks of the
Yes.
differential. There's a little mark of homework. There's
There was no differentials. There was this question about differentials. Well, okay, I can sacrifice the practice lecture and talk about differentials.
no, the homework we don't have it.
No.
what about
So that was the question mark because normally I told you I had planned 4 tests, which we will have, and 2 homeworks, which you did have. So we are having the 4th test next week,
Yeah.
the final test, the last one, not the final, but the last test.
And the homework? We don't have.
You already did your 2 homeworks. You already had 2.
No, for this derivative.
For this derivative, that was a question.
No, it's practice.
That was a question if we could have it, but you would still have to do the test.
Yeah.
so like we have 4 tests and that's it.
4 tests, 2 homeworks. Normally. That was my original plan, and then there was this idea floating around: what if?
What if what?
You tell me. So in the test, in the test for next week, what we'll have, you obviously need to find a few derivatives, something like 4 functions to derive. Then you will have to some tasks for applying the derivatives. It depends. I might give you one function to investigate and do all the derivatives and everything, or I might give you a separate task, take this function, find the minimum maximum points. A separate task, take that function, find the inflection points and concavity up and down. So I haven't decided yet. It's different every semester what I decide. And then of course we need one simple perhaps, but still a problem, a task of optimization. And let's have a look at that optimization problem. How do we apply derivatives in real life? Well, the answer is we don't. Some crazy mathematicians think we should.
And why the hell are we sitting here?
I don't know. Why are you? Okay, suppose we want to build this shed.
Do you need him?
Suppose we want to build this shed consisting of 3 separate rooms which are exactly identical, equal size. And we need, let's say, the total floor space 600 square meters. It's more or less a practical situation. So I need to store something. I need 3 compartments that should be of equal size, and I need to save money. So that means I need these 600 square meters, but I want to save money as much as possible on the walls. Which means I want the total length of all the walls to be as short as possible. And that's an optimization problem, a minimum problem. I want to, what I would like to find a function, for the total length of walls, and to minimize it, to find the minimum point for this, the minimum value for this function, because I want to have the least possible cost. The least possible cost. So obviously the width is W, and I might denote the compartment width by X, or I might denote this by X, and then there will be X, 1/3 of X, 1/3 of X, 1/3 of X. So now the thing is, we only can use one variable. Obviously I can write that width times 3x is this 600 square meters. It's the area that I have, or the area I must have. The problem is that it has 2 variables. And then of course I would like to find the wall length, or the cost function. In this example I multiplied by the cost, obviously. But it's possible to find the length function then in the end to multiply the minimum length by the cost per meter. And it's per meter because obviously the height will be what it will be. And if I have doors, they don't change anything because I do need a minimum of 3 doors to get in all 3 compartments. And the number of windows is up to me. I don't have to have windows. So for the optimization for this situation, what is important is only the total length of these walls. So the length of these walls, in this case it depends on 2 variables, which I don't particularly like. No, I don't like it, but still, the length would be 6x, no, 4, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4 W. Like this. I don't like this function being function in 2 variables. But I have this condition, I have this constraint, and from this I can, for example, express the width in terms of x. So if I choose each of these rooms to have the width x, I can find that then obviously the width of the whole shed would be 600 divided by 3x, which is 200 over x. And now I can put it in there, and my length will depend on x only. So my length function, okay, I'll write L of x is 6x plus 800 over x. This is the function of the total length of the walls, depending on how wide I choose each room to be. Obviously, there are some constraints. For example, if I must have at least 6 x's, then obviously the total length, 6x, should not exceed. It could be anything. It could be. All they have to be is positive. So I could make it like this, or I could make it like this, and have the same area. Then the question is, where is the golden middle that provides the greatest possible, the shortest possible wall length? So we have this function depending on how wide or how long I choose each section to be. Short, 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 long, long, long. Depends on this only, because the width, the remaining walling, will obviously depend on the total area. So now what I have to do is I need to find the minimum for this function. For what value of x will the total length of all walls be the least possible? So I need to find the minimum. So I need to minimize. I want to minimize the total length of walls so that I would have to spend as little money as possible. So how do we find the minimum of function? We derive it, we investigate the derivative, we find the minimum point. So the rest is calculus. This is modeling. This is setting up the mathematical model of the situation. This is clearly a modeling task. So now I start doing calculus, because up to now I was just setting up my mathematical model. Right. The derivative would be 6 minus 800 over x squared, which would be 6x squared minus 800 over x squared. So I say that.
Why with
What?
the second function? It's too complicated.
This? Probably because I would like to find the critical points, because I need to find the zeros. I would need to find the zeros of the derivative, so I would need this expression for the 6x squared minus the 800 anyway. I would need to deal with these anyway. Yes, it looks more complicated, but if I want to require it to be equal to 0, or perhaps at x is 0, it doesn't exist at all. But of course x has to be positive, because otherwise we'll have no shed. So now 6x squared minus 800 is 0, or x squared is 400 over 3. So x is positive or negative 20 over square root of 3. But of course we'll remember this. X has to be positive.
11.54.
Possibly. I solved it slightly differently. It seems I solved it slightly differently here, but the critical point x is exactly that. It's exactly this. So, yes. Now we have, of course, 0, which is actually a vertical asymptote for this function. The discontinuity of this function, we have this 20 over square root of 3. We have minus 20 over square root of 3 somewhere. I'm putting it there because I need to get the total picture. Sometimes I might just skip this part, but I still need to see the behavior of the function around this critical point, the positive critical point. So if x value is very, very large, then obviously this will be positive. And if x value is very, very small, then obviously this will be negative. So I can see that this is indeed the minimum point. This is indeed the minimum point. If I have misunderstood a problem sometimes, or if the problem, if I have set the problem wrong for you, for instance, or if the engineer or the merchant or whoever is concerned has misunderstood the problem and set up the function incorrectly, then it might just happen that we have, this is the maximum point, it's not the minimum. So now we have to investigate whether we made a mistake or whether we misunderstood the problem or whether the model is wrong. So yes, it might be that sometimes you see that you don't get what you want. It means there's some mistake somewhere. For example, this function has a maximum, it doesn't have a minimum. It's possible. So for this we can see that, obviously you said 11 point something, no?
Yeah, 11.4.
11.4 approximately. Okay, so it seems that, so, okay, 11.5. So it means that if I want to save money, I should take 11.5, 11.5, 11.5, and then compute the width, and I have my optimal size, the optimal measurements of my shape. And then of course I multiply the total, I find the total length, I put this into the original function, I find the total length, I multiply by cost per meter, and I get my costs. So it's more or less an economical problem, but it's also a geometrical problem, and there are a lot of problems where we use calculus in this way. It might be, for example, minimize the surface if the volume of something is given. For example, if you have a can of Coke, you know it needs to hold, let's say, half a liter exactly, and you want it has to be cylindrical, and you want to produce these cans, but you need to know the exact size so that you can save on material, to use as little material as possible, for example. On the other hand, you might have a certain amount of material and you want to enclose as large volume as possible, for instance. These are all optimization problems. Many of them are geometrical, but as many of them are economical. For example, in economics, you might encounter situations something like this with other kinds of functions, with other situations. How to optimize something, dealing with costs and everything else. Or we might simply have something abstract. For example, the fifth exercise, the sum of two numbers is given, it's 18. The sum of the first number squared and the second number doubled is the least possible. The fifth exercise. So it doesn't have to deal with areas or volumes or geometry. It could deal with numbers. There might be some situation. So the sum of two numbers is 18. So the first number is x and the second number is 18 minus x. I'm not even introducing another variable. The first number squared plus the second number doubled is the least possible. Alright, so this is the sum function, or you can use f of x, it doesn't matter what you call it. So this has to be the least possible. Again, we need to minimize this. Now this has an interesting result, by the way. So, okay, this is x squared minus 2x plus 36. The derivative is 2x minus 2. Is 2 times x minus 1. So we can see that the critical point is 1. And the derivative is positive if x is greater than 1, negative if it's less. And the task states nothing about positive or negative numbers, any numbers. And you see what? And you see what? We can say that this sum will always, for any numbers, It doesn't matter, the sum doesn't matter. Such a situation will always be, such a sum will always be the minimum, the least possible, if one of the numbers is 1. So if you have a given sum, for example, the sum of two numbers is 100. What are the numbers if the sum of the first number double, first number squared and the second number double is the least possible? You see, 18 appears only in this place. When we derive, it doesn't influence the derivative. So whatever the sum you require, one of those numbers will always be 1 in this situation. That's an interesting one. That's an interesting situation. But so, in this case, it should be 1 and 70. Or if the sum of those two numbers is 100, then it would be 1 and 99. Which is well, it seems strange at first. All right.
And what was the result?
The result?
Yeah.
The result,
meaning of the one.
find these numbers. So, okay, x is 1, and obviously the second number, 18 minus 1, is 17. So those numbers are 1 and 17. That's the answer.
The lowest, the quantity of these numbers.
Yeah, no, it's-
Yes.
Okay.
Okay. What else? I think number 7 could be familiar, or should be familiar. So we have a rectangular plate of tin, and we want to cut out square corners and then fold up the sides to get, let's say, a baking pan or something.
it's like primary school.
Yes, 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 exactly. And what is the size of those squares to be cut out if we want the maximum volume for this? So we have, yes, okay, I have a sheet of paper and I want to cut out squares in the corners so that I can produce a little nice box with the maximum possible volume. So this is actually the problem. This is the task. So we have 25 in width and 40 in length. And then of course the size would be x by x for these squares. And we need to maximize. Now this time we need to maximize. In these two tasks we had to minimize something. Now we need to maximize, find the maximum volume, or just figure out what is the x value, how large those squares should be to get the maximum volume for whatever purpose. For whatever purpose. Well, you are making a cardboard box because you want to give your friend some, I don't know, candies, and you need to make that box as large as possible because you are generous and you want to give your friend lots and lots of candies.
Or opposite.
Or the opposite. Well, then you can cut out, well, almost nothing, of course. Then again, now in this case, x should be, well, it's obviously positive, but there is an upper limit. X couldn't be, x should be less than half the width, because otherwise if we cut out everything, there's nothing left. So it should be less than 20.5 centimeters. So there are some limitations, some constraints. So now what we have is the volume of this new box would be, the length is 40 minus 2x. The width of the base remaining is 25 minus 2x. The height will be just x. Okay, so this is the volume function. This is the volume function, and well, obviously we should try to simplify it for the sake of deriving it more easily.
Minus 2x is minus the
Okay, 2, 4x cubed. Now there 130 x squared, and 40 times
1,000.
25 is 1,000, so it's plus 1,000 x. Okay. So this would be the formula for the volume. Now we derive it. And it's 12x squared minus, I don't like it. There's something wrong with this. Okay, alright, I can take out 4. So I have 3x squared minus 65 minus 250.
Okay,
Plus, sorry, plus.
The answer is 116 and 1
75.
I calculated this. 16 and 5.
16 and 5?
Yeah.
You forgot the x after.
Yes, I noticed. But I don't see where I might get 16 and 5.
Like
There's something, okay.
minus-
It is minus 50,
Minus
minus
4.
80, it's 130, that's correct.
Minus 4x in the power of 3.
40.
It must be minus.
Uh,
Plus.
Final plus in the middle is minus. Minus and minus is minus. Should be.
well, you can write the root, which is
Yeah.
260 plus minus square root 260. Yeah.
Okay.
You know the formula.
So anyway, anyway, the two roots will obviously be positive. One root, another root. The two roots.
16.67.
This.
Yes, 16.67.
So 16 and 2/3. All
Yeah.
right. And this is 5. Yes, that sounds. That's more likely. Okay. So for very large and very small x values, it will be positive, and for medium x values, it will be negative.
Of course, we should use the 5.
Yes, so yes, of course. And by the way, because of this also, and then, well, actually, it would be the minimum possible value. Obviously, it would be negative. Negative volume. That sounds scary, like a black hole into which everything falls and nothing comes out. So x is 5, so this means that we have to cut out neat corners, 5 by 5 in each corner, nice squares, and we might even put 5 into the original function and find the maximum possible volume that you can get. Alright, is there anything else from this paper that we should discuss now? Because I'm more or less.
It's 5 over the squares, yeah?
Yeah, 5.
So it's 5 by 5 squares in the corner. See what I denoted by x. X is that. So x is 5. If x is 5 centimeters, in this situation, if I cut out 5 centimeters square in each corner, then I can get the maximum possible volume for this thing.
Why, if the cutting is, must be maximum, the volume must be the minimum. If you cut with the maximum value.
If we want to get the maximum volume of one sheet of paper, then 5 centimeters is what we cut out in the corners. And if I put x into the volume function in there, I can find what that volume is. I can put x equals 5 here, and I can find the value. So it's 30 times 15 times 5. 30 times 5 is 150, times 15 is cubic centimeters.
So anyway, it should be less than 12.
Yes, because you see you can't go longer than this. So it's from geometrical and realistic considerations. So what we should consider is obviously just this part. Fortunately, we do have the maximum in there.